right, so today we're going to look at 1.5, which is on transformations of quadratics. We're going to study transformations with every kind of function we do. We're going to do logarithms, we're going to do rational, radical, exponential, all in different chapters. But one thing that's the same that we always look at is how can you transform the function we're studying. Transformations include shifting up and down, left and right, those are your shifts, reflecting over the x or the y-axis, or stretching, either stretching or compressing vertically, or stretching and compressing horizontally. We're going to look at most of those transformations, but we're going to start out by looking at them with parabolas. So remember that if you have a parabola, that's a quadratic function, generally written in the form ax squared plus bx plus c. At least that's the way you see it when you're getting ready to factor a problem, or if you want to use quadratic formula. That's the format that you want. Everything on one side, 0 on the other. So and it is important to remember what a, b, and c are. A, b, and c can be any number that you want, real numbers, except a can't be 0. That's what that's saying. So a, b, and c are elements of the real number system. That's what that symbol means, element of, it's like a backwards looking E. But a can't be 0. Yeah?
Is there no way to rotate a function?
Yes, you can rotate functions. That gets into using a little bit of trig.
Yeah, but you said that
But yes, you can rotate a function using what's called a matrix. So if you look up, like if you do any kind of computer graphic design and you look up rotating functions, you'll probably see a matrix with like sines and cosines or tangents in it. A little bit beyond what we're doing. But yes, it can be done. A lot of times though, if you rotate something, it's no longer a function. Think of like a parabola.
If you bring it to the side, unless it's like a 180 degree.
Yeah, if you did. Yeah, if you reflected it that way, like rotate 180.
Rotating 45 degrees.
But that fails the vertical line test. So now it's no longer a function. Why can't a be 0? What would happen? Yeah.
The x squared would be eliminated.
Yeah, if you make a 0, you just eliminated the quadratic term. Now essentially you have y equals mx plus b. Now it's linear. So to be quadratic, the a value can't be 0. So let's look at what happens when we graph y equals x squared. So if you have anything else in there, you can clear it. Type in x squared. Standard window will be fine for the zoom. So let's do that. And there you go. That's what you get. So basically what we just graphed is this. What does that mean to do now? We talked about that a couple days ago, I think. Yeah?
Does it mean that whatever, like the y would be negative, so that you just move it over?
So like if you saw this, what does this mean to do?
X equals h2.
So yes, replace the x value with a 2. How about in this one? What are we doing? Well, something might happen, but what are we actually going to write down on the right hand side? Yes? Can you be a little more specific? Just like this?
The negative, like parentheses, negative outside and x squared inside parentheses.
Okay, so I like the idea of using parentheses. We do have to do that. But when you substitute something in, which that's what this means, substitute this in everywhere you see a variable. Whatever you're substituting in, that whole thing is in parentheses. So like if I was going to substitute in a 2, it would be this. Parentheses don't really make much of a difference. But if it said to do this, then I would do that. Okay, that negative and the 2 are getting plugged into the squaring function. In this case, it's the negative and the x. How do you think that's going to look when I sketch the bottom one compared to the top one?
The exact same.
It is. It's going to be exactly the same.
Yeah.
Why? I'll just do it real quick. While I'm sketching it, why does it come out exactly the same? Right. Okay, I don't know if you can see it, but it did trace over it in red,
Oh, yeah.
very faintly. But it is the same graph. And that's because we did a reflection. But we did a reflection over a line of symmetry. So the difference here, in this case, is none. There is no difference between f of x and f of negative x. But in general, what we just did was called a reflection over the y-axis. We reflected the graph over the line of symmetry. Anytime you do a reflection over a line of symmetry, you can't tell that you did it. Now, one feature that a parabola has that a line, and most other shapes don't, is a vertex. So the vertex is the lowest point or the highest point of your parabola. The way it would be the highest point is if you flipped the parabola vertically, or you flipped it over the x-axis. Any questions on that?
Well,
Yes. This is more out of like clarification. There's a word for like when you reflect something or rotate something like the second drawing on a graph. Do you know what that's called? I don't know if it makes sense.
The image, or
Oh yeah.
maybe the image under a certain transformation. I'm not sure if that's the word they use. Image.
Maybe image. Okay.
Pre-image, post-image. I'm not sure. Yeah. I know sometimes if you have a point, like in geometry, and that's point A, and you transform it, then you call this point like A prime. I know sometimes you see something like that for an individual point. But that's all I could think of.
Okay, thank you. Yeah.
All right, so let's see what happens if we change the A value. Okay, that's the number that's in front of x squared. Okay, I want to see what the effect is on the graph. So let's put in x squared, I already have. Let's do 1/3 x squared. And let's do 2x squared. All right, so I typed in everything I had up on the board. And we'll hit graph and see what it looks like.
what was the second, the last one?
2x squared. So what does it look like the effect of A is? If you change the A value, what does it do to the parabola? There's a couple ways to actually think about it. You can either think about it in like a horizontal way, or you can think about it in a vertical way. Yep.
It like widens it, kind of like, so it's, yeah, I don't know, it's not the best way to explain it.
Yeah, it affects the steepness of.
Yeah, so it does have an effect on the sides of it, like how wide it appears or how steep the sides are. So if you imagine this parabola was like glued down at the origin, right, and it was made of flexible material. If you pulled up on the sides, right, that would be a vertical stretch, and it would get skinnier. Now think about, again, if it was glued down and you push down on it, well, the parabola is going to start to spread out because you're squishing it down. So the effect of changing A, we either call it a vertical stretch, or we could call it a vertical compression. Okay, that's how you can describe what A is. Specifically, if A is a value that's bigger than 1, like it was in this last one, 2x squared. That's the black one. It stretched it.
Alright, so changing A in that. Okay.
If a is a fraction between 0 and 1, like 1/2 or 1/3 or 0.6, something like that, that's going to cause the graph to shrink vertically. Now, to keep it simple when we describe it, we can always just use the word stretched. I just want you to understand that if I say something like, this graph has a vertical stretch by 1/2. If I say vertical stretch by 1/2, you should really understand that what that means is it's compressing because you stretched by 1/2. It's kind of like I said, if I'm going to give you a raise of half your salary. How's that work? You're not really making more, you're actually getting less because it's a fraction.
You keep it up from there.
So notice all these a values we just looked at were all a values that were positive, either greater than 1 or between 0 and 1. If we start to look at what happens with a negative, what do you think the negative is going to do?
Is it going to be the same effect of changing it? What do you mean?
Well, what's going to be the effect of putting a negative number in front of the x squared? Like if I compared positive 2x squared to negative 2x squared. And this is a little different than doing this. We already did that. That negative is not part of what's being squared. Yep.
I flips it like instead of going with the parabola facing up, and now faces down.
Right. It's going to be a reflection over the x-axis. So if one of your graphs looked like this, by putting a negative in front and not putting it in parentheses, it's going to make it look like that. So the point is, a negative causes a flip or a reflection. If it's in parentheses and part of what's being squared, it causes a reflection over the y-axis. If it's in front and it's not being squared, it's not inside the square function. Right? This is the squaring function in that problem. It's just being applied to x. It causes a reflection over the x-axis. And you could do both. If you wanted to reflect something over both axes, you could do something like negative 3x squared. The negative inside the squaring function causes a reflection over the y, which wouldn't do anything for a parabola. And the negative outside causes a reflection over the x, which would do something. Any questions on that?
And do the stretches still apply?
Yes. So in this particular problem, there are two transformations here. Vertical stretch by a factor of 1/3 and reflect over the x-axis. You read this negative and this 1/3 as two separate things. Basically tells you how to do this one. So if I had the graph of y equals x squared, I want to know the two transformations I would have to do to turn it into the graph of negative 5x squared. Well, first, how many transformations are taking place? Yeah? Two. Let's start with the 5. How do you describe what the 5 is going to do to the graph? Yeah?
It's a shift, right?
No, we haven't done a shift yet. Shifting is with adding and subtracting. Stretching is always with multiplying. Okay?
Since it's greater than 1, you go to stretch vertically.
So vertical stretch. And now we have to say by how much? By a factor of 5. Yep, that's a vertical stretch by a factor of 5. And what's that negative going to do? Yep. That's going to reflect over the x-axis. So the order that you do the transformations in is important, and it's going to be similar to like PEMDAS. Right? There's an order we have to follow. But any questions on that? When we have more transformations in the problem, like shifting and stretching, I'll show you guys the order. Okay, kind of already gave this away when I answered one of Kian's questions, but adding and subtracting, what kind of transformation do you think this is going to be? Yeah.
Makes it go up and down.
Can you be more specific about the type of transformation that would be called? Shift. I do agree. It is going to be a shift, and this one is going to be up or down. What do you think a +2 would do? Shift it up 2 or down 2? Jessica? Yeah, it would. It would move it up. So I'll just do the first one. So to get y equals x squared plus 2 from y equals x squared, you would shift y equals x squared up 2. That's how you would do it.
Alright, so there's only one change.
There is only one transformation in each of those. How about x squared minus 3? You take y equals x squared and do what with it? Xander? So if you wanted to transform y equals x squared into y equals x squared minus 3, what would you do?
Bring it down.
You'd shift it down 3 units. Yes. Make sure when we talk about shifting, always use a positive number. Don't say like shift down -2. That's kind of confusing. Just say shift down 2 or up 2. Okay? Down would take the place of this word of the negative. So these are both examples of shifts. These are rigid motion transformations, which a stretch is not. Rigid motion means it takes what you have and literally copies and pastes it somewhere else. It doesn't distort in any way. If you add a number to x squared at the end, it's going to make it go up. If you subtract a number, it's going to make it go down. And notice what I said here. Don't say like shift down -2 units. It's just down 2 or up 2. Okay, down is the negative. So adding or subtracting on the end of the function moves it up and down. How do you think you would move it left or right?
Wait, what is that? Is that x squared plus a?
Yes. Yep, Jackson?
I don't exactly remember. I think it's like the same thing, that there's parentheses around there.
There would be some parentheses involved, yeah. Yeah.
Maybe parentheses, like an opening parentheses, and then x squared, and then like a plus or negative, and then closing.
Okay, so it is going to have the adding or subtracting in the parenthesis. The square is still outside. So if you did something like that, that will cause a shift left or right. Adding and subtracting is always a shift.
Oh, wait,
Now, the question is, when you're shifting left and right, which way do you think plus would shift it? Like x plus 2. Which way do you think plus 2 is going to move it? Yeah?
It goes left.
It does. It goes left. It does the opposite of what you would expect. All right? When you see a minus, it's going to shift right. Try it. If you graph it on the calculator, that's what ends up happening. So I'll do the first one. So to get y equals x minus 3 squared from y equals x squared, y equals x squared is called the parent function. It's the basic function you're starting with. So they call it the parent function. So to get y equals x minus 3 squared from the parent function, shift y equals x squared, right 3. If you wanted to get the x plus 2 squared, you would take the parent function and shift it left 2. So this, again, is another rigid motion transformation. It doesn't cause any distortion.
Alright, so you said that if it's positive, then it would be left.
Yeah, I'll write that down.
Okay.
I'll write down which way is which. So I think I'm going to write it this way. So rigid motion transformation. If you have x minus, and then you have a value, this will shift. Minus goes to the right. Normally you would think minus would go to the left. You think of a number line.
Yeah.
But it doesn't work that way. If you have x plus, and then you have a value, plus is going to shift left. And as always, we don't want to say shifting left or right by a negative amount. Always, you can shift left 5 units, you can shift right 5 units. But don't ever describe a transformation as shifting left negative 5 units. That just gets confusing. So now, let's think about the vertex. If you have y equals x squared, normally your vertex is right at the origin. The only thing that affects where the vertex is going to go is shifting left and right or shifting up and down. That's all that affects it. So if you want to know where this vertex is going to be, first you take into account, did you move left or right? You look at your problem and say, okay, do I have a number inside parentheses with addition or subtraction? That's going to help you figure out the x value of your shifted vertex. Then, look at your problem and say, did I add or subtract anything on the end? That's going to help you find the y value. So remember, what variable did I use? K is controlling the y value of your vertex. And I need a letter for this one. Let's use H. I don't know if I wrote it down anywhere. No. So let's use H. So H will control the x value of your vertex. So to figure out where you've shifted to, as long as you know this value right here and that value right there, that's all that affects the location of the vertex. The H and the K. Now, notice how this is written. X minus, and it's the number after the minus sign. In this problem, my H value is 3. X minus, and it's the number after the minus sign. It's a 3. What's the number after the minus sign here? Negative 2. You'd have to think of it this way. The H value is always the number that's inside after the minus sign. Because this means you went left 2. So it has to be a negative. Okay? So be very careful if they write it as x plus. That can be a little tricky. Now, how about the line of symmetry? What kind of line of symmetry does a parabola have? Is it horizontal or vertical? Vertical. And vertical lines always start out how? X equals. And think about the transformations. A line goes up and down forever. What type of shift would have no effect on a line of symmetry?
Oh.
Yep.
Like for this particular case.
Any parabola.
Sorry.
Yeah. A vertical shift has no effect on a line of symmetry at all. Line of symmetry goes up and down forever. If you shift it up a little bit, it still goes up and down forever. So the only value that affects the line of symmetry is your left and your right movement. That's the H value. So that's how you can find the vertex and the line of symmetry using the H and the K values. Let's try it. Here's a problem. And it says find the vertex and line of symmetry. What's the H value in this one? Yep. -2.
But you said the line of symmetry was? Sorry.
X equals K.
X.
So the vertex has been shifted left 2 units. So H is -2. If you get confused, think of it like this. X minus.
Wouldn't the line of symmetry be X equals H? Because H is X.
Yeah, did I write X equals H? That's what I
No,
meant
you
to write.
just said it.
Yeah, so X equals H.
Oh, okay, alright. I wrote.
Did I say K? I'm
Yeah,
sorry.
you
Yeah.
said K.
Sorry. No,
Yeah.
Sorry.
X equals H. So we've shifted left 2, because that's the number after the minus sign. And then how about my K value? Yeah. -3. There's nothing tricky about the K. It's just whatever number is at the end. Now the line of symmetry, as Jessica just said, is X equals H. In this case, X equals -2. Any question on that? All right, so we need to talk a little bit about the order. Okay, when we do transformations, it is like PEMDAS, and order makes a difference. So when we have a problem with multiple transformations, yes, that's the order you follow. So in a problem, the first thing you always deal with is a horizontal shift. If you had a horizontal stretch, you would deal with that next. We're not doing those with parabolas. That's why I didn't really include it. But if you wanted to include horizontal stretch, it would be right there. But we're not doing it with parabolas, so don't worry. The next thing you would deal with, so this is the stuff that's inside the squaring function. You just dealt with the minus h, or plus h if it was, if it was a plus. The next thing we deal with is the vertical stretch. That's when we have a number multiplied in front of the squaring function. It's not inside the squaring function.
Oh, wait. Alright, can we go over the problem?
Vertical stretch? Yeah. I think we did one like this. Maybe it was 2x squared instead of 3x squared. If there's a negative with the number in front,
Yeah.
that would be a reflection. And I put if necessary, but these are all if necessary. You may only have a vertical shift in your problem. You may not have the other three. And vertical shift is always the very last thing you would deal with. And these could be plus or minus. And in general, we used, I think, the letter A to represent a vertical stretch.
Alright, so what did you say about horizontal stretches?
Horizontal stretch would be right here.
Okay, well.
If I multiplied x by a number, but we're not going to do that.
Alright, and what's that formula in red for?
That's just the general form that shows you each transformation we studied. Horizontal shifts, vertical stretches, reflections, and vertical shifts. So horizontal, vertical stretch, vertical reflection, vertical shift. So let's try one where we go through the values and see if we can describe the transformations. Okay, how many transformations would it take to turn x squared into 5x squared plus 4? Yeah, John? 2. Can you tell me, going in this order, do we have a horizontal shift in that problem? No, that would be in parentheses. We don't have that. Do we have a vertical stretch? That would be the next one. Yes. How would we describe the vertical stretch? Yeah.
Shift 4 units up.
Wait, what are you describing?
Oh, vertical stretch, my bad. Sorry. Someone else needs.
Yeah, Ben?
Stretch by a factor, right?
Yeah, just make sure you say which type of stretch, because we do have horizontal and vertical. I know I said we're not doing horizontal, but we're going to eventually. Just make sure you say vertical. So vertical stretch by factor of 5. And then the second thing that Geronimo just said, shift up 4, perfect. That would be your last. Alright. Let's try this one. So negative 3 times x minus 1 squared plus 4. How many transformations in that one? And assume y equals x squared is the parent function again. Yeah.
4.
Yeah, it's 4. Okay, anybody tell me the first thing that we would do to turn y equals x squared into that? Yep. Yeah.
Shift left 1.
It is a shift, and it is 1 unit, but it's to the right. So remember, whenever you have x minus,
Oh, true.
that's going to be a shift right. X minus always moves right. X plus would be left.
The parent function has, or the parent function doesn't have an h, but when you write the full formula, it goes open parentheses x minus h. Yeah.
Yeah, this is like your h value, x minus h.
Okay.
So your h value in this case is a positive 1.
Oh, well, thank you.
So shift right 1. Okay, next thing you would do?
Alright, can we just write 1 or do we have to do like units or whatever?
You can just write 1 because we don't know if it's feet or inches. You don't have to put units. No units. Next thing. Yep, Angela?
The vertical stretch.
Yep.
Well, shrink, I guess. It's negative 3 today.
Does a negative cause a shrink?
Oh. Wait. Is it backwards? Negatives make growth and positives make shrink or something.
Just worry about
Negative doesn't really have anything to do with whether it stretches or compresses.
Oh.
Negative is a separate transformation. We don't have to worry about the negative in this step.
Oh, okay. So then it's just a stretch backward.
Vertical stretch by a factor of 3. Now we want to worry about the negative.
Oh.
What does the negative cause the graph to do?
Oh, that's what makes it like flip, right?
Yeah, specifically over the x-axis. You could also say vertical reflection, that's the same thing. So reflect over x-axis. And Leva, what's the last thing we would do? Well, what number haven't we used there yet? The 4. Do you remember what the plus, specifically it's a plus? Right, we add or subtract outside of the square function, which is outside the parentheses, it's a vertical shift. So it's shift up 4. Now, in a problem like that, it's easy to see what the transformations are because it's written in this format. Now, if you took this and FOILed out x minus 1 squared, multiplied by negative 3, and then added 4, you would get something that I talked about at the beginning, like this. Well, that's no good. Okay? If somebody FOILs it out and writes it in the form ax squared plus bx plus c, and it's not written in something like this form, it makes it very hard to figure out a, h, and k, which means you can't really figure these out. So all the problems we've had so far have been in what we call standard form. If somebody does all that out, it's going to have to be fixed back to standard form. So if you had a problem, I'll show you the problem, and then I'll show you how we fix it. But if you had something like this, 3x squared plus 12x minus 18, you cannot tell what the shift left and right is, or the stretch, or the vertical shift, or if there's a reflection. It's not in the right format. So in order to get it back into standard form, we have to do something called completing the square.
Oh, that sounds familiar, and I don't think it's a good
Well, I'm going to show you. It's not really that hard what we're going to do with it, but it definitely is going to probably take some remembering, because there's one step you have to remember how to do. So the goal with completing the square is to take something that's in ax squared plus bx plus c and make it so we can see the transformations. The most important thing is to keep your equation balanced. So if you do anything to the left, make sure you do it to the right. You have to be very careful when you do that. So I'm not going to really write a whole set of steps for completing the square. I'm going to show you an example, and I'll make a few notes as we go through it. We're going to look at that. 3x squared plus 12x minus 18. I don't really care if we describe the transformations right now. I'm sure once we complete the square, you could do that. I'm more just concerned with showing you how to complete the square.
So does it, if it's given in that form, you have to use completing the square?
Yep. If you're given something in that format, you have to fix it. Okay, so there's a few steps you have to follow to get something in that format. The first thing you always want to do is put the constant on the other side. Put the constant alone. That's step 1. So we're going to have 18 equals 3x squared plus 12x. So I'm just going to say isolate the constant. The next step is to complete the square. The coefficient of the x squared term has to be a 1. It can't be anything besides a 1. What's the coefficient of my x squared term right now? 3. I don't want a 3. So I need to pull the 3 out, but it only affects the right-hand side. It doesn't affect anything on the left. What do I get when I take the 3 out, or factor the 3 out on the right? Yeah, Jack?
X squared plus 4x.
X squared plus 4x. So this step is make coefficient of x squared equal to what?
Wait, so what was the constant in that case?
18,
Okay.
when we move it to the other side. It was negative 18.
What's constant?
Constant?
Okay, alright.
Term without a variable.
Okay, thank you. Sorry.
No, that's fine. Now, those two steps are pretty common sense. The next step is like the magic step. It's the step that completes the square. And unless you knew what to do with this step, you can't really just guess at how to do it. So, what we're going to do now is we're going to add something to both sides. So I'm going to leave a little bit of space to do that. And what I add to both sides has to do with that number. That's the linear coefficient. It's the coefficient in front of the variable with an exponent of 1. So what you're going to do is take half of the linear coefficient and square it. And then add that to both sides. That's the step that completes the square. The whole goal in completing the square is to make it so you can factor something as like x plus 3, x plus 3, x minus 5, x minus 5. We're trying to force something to factor into two identical terms. Or binomials, two identical binomials. So, my linear coefficient is 4. What's half of 4?
2.
And what do you get when you square it?
4.
4, so nothing interesting happened that time, really. If this was a 6, half of 6 would be 3. 3 squared would have been a 9. Now, what did I just add on the right? Yeah?
4.
Didn't technically add 4 on the right. Okay?
12.
I added 12. Because anything I put inside this parenthesis is tripled because of distributive.
Oh.
So what you want to add on the left is 12, not 4. Sometimes that step doesn't happen. If you didn't factor a 3 out to begin with, then yes, if you had added 4 on the right, you would add 4 on the left. But you didn't really add 4 on the right, you added 12. That's how you keep it balanced. Now, simplify 18 plus 12. And x squared plus 4x plus 4 should factor very nicely into two identical things. And now you're going to start to see it look more like this. Something times something squared. How does x squared plus 4x plus 4 factor?
X plus 2 and square.
Right. It's x plus 2, x plus 2. And the last step is reversing what we just did. Put the constant at the beginning. Put the constant back on the other side. Now we can see pretty clearly there are 3 transformations. Shift left 2, vertical stretch by a factor of 3, and then shift down 30. You couldn't see that before you completed the square. Like if you go back and look at the original problem, where's the 30? There's no 30. It just happened because we completed the square.
Oh, okay. happened with the, never mind.
So at this step, I didn't really write down what I did, but I guess I could say I simplified 18 plus 12. So simplify, and then I factored. And then in the last step, I put the constant back on the other side. Move constant back with the other stuff. I'll just say in this case, I moved it back to the right. And not something we do a lot, so a lot of people don't remember how to complete the square. Hopefully that helps. And this is the most important step.
Alright, what's the linear coefficient?
The number in front of x.
Square.
Okay, I don't want to do that.
Wait, alright, when did we square the linear coefficient at? Wouldn't that be 9?
So if you take half of this, it's 2, and then if you square 2, you get 4.
Oh, that one. Okay.
So when you have something in general form, again, I don't like it to describe transformations, but it's not always a bad thing. Right? This is A, this is B, and this is C. Does anyone remember in the quadratic formula, what goes under the root? Yeah?
Isn't it B minus 4AC?
Close, yep. Right. And remember what we learned about square roots. When you're dealing with real numbers, how do they have to come out?
Positive.
They have to come with 0 or positive.
Yeah.
So if you know this value, and this value, you can very quickly determine.
Is this just like a different way of doing it?
So it's not actually finding an answer. It's just telling you how many answers the problem would have. So if you calculated the b squared minus 4ac, and it came out to less than 0, what that would mean is if you tried doing a quadratic equation on this, the square root would come out imaginary. Essentially, that would be a graph that looks like this. It's a graph that never crosses the x-axis, which means we say that it has no zeros. A 0 is where it crosses. If you did b squared minus 4ac and it came out to exactly 0, that would be a graph that looks like this. Touches the axis in one spot and then goes back up. Or it could go down. But the point is, it touches the axis once. If you tried the b squared minus 4ac and it comes out greater than 0, that's this case, where it crosses the x-axis twice. So all this b squared minus 4ac trick is telling you is how many times your graph crosses the x-axis. Another word for that, how many zeros does your graph have? It doesn't actually find them for you. This is only part of the quadratic formula. If you want to actually know what the 2 zeros are, well then you got to do the whole quadratic formula. But if you just wanted to know how many, you can do this quick check and see if it's less than 0, equal to 0, or more than 0.
Wait, what would we use that for?
To determine how many roots a graph has, or how many times it crosses the x-axis.
Oh, okay.
Specifically for quadratics. That's all it's for. Right, so that pretty much summarizes what we're going to be doing with quadratics for now. Okay, so homework tonight, just one page because we only did one section. I think it's 15 or 16 questions. So I'll make sure I put the video online so you guys have that. Don't forget, from lunch, you are going right to the auditorium today because you have the assembly. You're not going to your second period class, but from what I've been told, it's not going to take more than probably a half hour.
No.